Welcome back to our channel, where we journey through the cosmos, uncovering the latest discoveries and exploring the mysteries of space. Today, we're diving into a groundbreaking revelation that might just unlock one of the greatest secrets in planetary science. Have astronomers finally discovered the secret recipe for the rapid growth of giant planets? Let's delve into this fascinating new research that could reshape our understanding of how worlds are born and evolve. For centuries, scientists have been piecing together the puzzle of how planets form, grow, and evolve in the vast reaches of space. We have a fairly solid grasp on how the rocky inner planets of our solar system, Mercury, Venus, Earth, and Mars, came to be. These terrestrial planets formed through the collision and accumulation of smaller bodies, known as planetesimals, over millions of years. However, the same process doesn't fully explain the formation of the solar system's behemoths, the gas giants Jupiter and Saturn, and the ice giants Uranus and Neptune. These massive planets formed far from the Sun, where conditions are much different and less conducive to rapid growth, according to previous models. The distances involved are staggering. Jupiter orbits 15 times farther from the Sun than Earth, and Neptune is 30 times farther out. At such vast distances, the solar system's outer regions have much less material and much weaker solar radiation, which should, theoretically, slow down the process of planet formation. Yet, here they are, huge, magnificent, and defying previous expectations. This paradox has left astronomers scratching their heads, leading to the development of new theories and models over the years. Enter a team of scientists from the Origins Excellence Cluster, the Max Planck Institute for Solar System Research, MPS, and the Ludwig Maximilian University of Munich, LMU. These researchers have developed a new model of planetary evolution that might finally explain the apparent discrepancies in the formation of these outer planets. They believe they've discovered a crucial, missing ingredient that could accelerate the growth of giant planets, even in the cold, distant regions of a solar system. The team's simulation is groundbreaking because it's the first to incorporate all the physical processes necessary for planet formation in one cohesive model. According to this new research, disturbances in the disk of gas and dust around newborn stars, known as protoplanetary disks, might trigger the rapid formation of giant planets. This theory aligns well with recent observations of young extrasolar planets, or exoplanets, suggesting that giant planets can form much faster and more efficiently than we previously thought. But let's take a step back and break down what this all means. When a star is born, it forms from a dense cloud of gas and dust in space. This cloud collapses under its own gravity, eventually igniting nuclear fusion in the star's core, a process that will sustain it for billions of years. However, not all the material in this cloud becomes part of the star. Some of it remains in a rotating disk around the star, which is where planets are born. In these protoplanetary disks, dust grains collide and stick together, gradually forming larger and larger bodies. Over time, these bodies can grow into planetesimals, rocky or icy objects that are the building blocks of planets. For the inner rocky planets, this process is relatively well understood. However, when it comes to gas giants like Jupiter and Saturn, the traditional model has some significant gaps. The new model proposed by the Origins team suggests that in the outer regions of the protoplanetary disk, millimeter-sized dust particles accumulate in specific areas due to aerodynamic forces and turbulence. These particles clump together, forming larger structures more quickly than previously thought possible. This is crucial because, according to this model, the presence of these dust traps can prevent the dust from spiraling inward toward the star, allowing it to accumulate in a small region of the disk where a planet can form. As these planets grow, they begin to exert their gravitational influence on the surrounding gas and dust. This can create new regions of dust accumulation farther out in the disk, potentially leading to the formation of additional planets. In essence, the formation of one giant planet can trigger a domino effect, leading to the formation of others even farther from the star. This could explain why our solar system has multiple gas and ice giants, all orbiting at great distances from the Sun. What's truly fascinating is that this model also suggests the possibility of planets forming at distances up to 200 times farther from their star than Earth is from the Sun. This is well beyond the current location of Neptune, and it challenges our previous understanding of where and how planets can form. The implications of this discovery are profound. Not only does it provide a potential explanation for the formation of our own solar system's giant planets, but it also offers insights into the diversity of exoplanets observed in other star systems. Over the past few decades, astronomers have discovered thousands of exoplanets, many of which are gas giants orbiting far from their parent stars. These discoveries have puzzled scientists because they don't fit neatly into existing models of planet formation. However, this new research could help bridge that gap, offering a more comprehensive understanding of how planets of all sizes and types come into being. Let's also consider the implications for our understanding of the early solar system. The formation of Jupiter and Saturn likely had a significant impact on the development of the entire solar system, influencing the orbits of other planets and the distribution of smaller bodies like asteroids and comets. By understanding how these giants formed, we can gain new insights into the history of our own planet and the conditions that made life possible on Earth. The results of these simulations have been validated by observations from the Atacama Large Millimeter, Submillimeter Array, ALMA, a powerful observatory located in northern Chile. ALMA has been instrumental in studying young planetary systems, and its data has provided crucial evidence supporting the idea that giant planets can form much more quickly than previously believed. This alignment between theoretical models and observational data is a significant step forward in planetary science, offering a more unified view of how planets form and evolve. But the journey doesn't end here. As with any groundbreaking discovery, this research opens up new questions and avenues for exploration. For instance, how common is this rapid planet formation process in other star systems? Could there be entire populations of giant planets in distant, cold regions of space that we have yet to detect? And what does this mean for the potential habitability of exoplanets in systems with multiple giant planets? These are the questions that will drive future research in this field as scientists continue to explore the incredible diversity of planetary systems in our galaxy. The answers could have profound implications for our understanding of the universe and our place within it. In conclusion, the discovery of this secret recipe for rapid planet growth is a major milestone in our quest to understand the cosmos. It challenges long-standing theories, offers new insights into the formation of giant planets, and could reshape our understanding of the early solar system. As we continue to explore the vast reaches of space, we're reminded that the universe is full of surprises, and that every new discovery brings us one step closer to unraveling its deepest mysteries. So what do you think? Could this be the key to understanding how giant planets form? And what other mysteries do you think the universe has in store for us? Let us know your thoughts in the comments below. And don't forget to like, share, and subscribe for more videos on the wonders of space. Thanks for watching, and we'll see you next time as we continue to explore the cosmos.